Assalamu alaikum. In this video, we will discuss Thomson's method to determine the specific charge of electron. Before going ahead, let me tell you what is specific charge. Here, specific charge means the charge per unit of mass. Charge per unit mass. It means dividing the charge of something by its mass. So when I say specific charge of electron, it means dividing the charge of electron by its mass. So specific charge of electron is nothing but dividing the charge of electron by its mass. Usually it is represented as E upon M, something like this. Now, to determine the specific charge of electron, Thomson used a specially designed discharge tube. Already we have learned about discharge tubes. Discharge tubes are usually cylindrical in shape and they are made of glass. Sometimes they are filled with a gas or they are evacuated completely. Okay, and apart from this, they comprises of two electrodes. Now let me show you the shape of discharge tube used by Thomson in this method. At one end, the discharge tube is in the form of a cylinder, whereas another end is broadened to appear something like this. It is broad. It has got a flat end. Okay, this a flat end. This complete setup is made of glass and it is evacuated from inside. That means there is no air or gases present inside this discharge tube. This is a flat end. The inner surface of this flat end is coated with some fluorescent material like a zinc sulfide. We know whenever a cathode ray, electron beam or some rays fall on fluorescent material, it produces light. Okay, so the same thing happens here as well. At this end, there is a filament which is connected to a low tension battery. This is a low tension battery. Here tension stands for voltage. Okay, then in front of this there is a cathode. There is a cathode here. When electric current is passed through this tungsten filament, it emits out electrons. Due to thermal emission, it becomes red hot and it emits out electrons. And we obtain a beam of electron. This beam of electron is referred as a cathode ray. The stream of electron is usually referred as cathode ray. Okay. Then one thing I forgot to mention. Apart from cathode, there is an anode is present here. This anode has got a fine hole at the center. There is a fine hole here. So this cathode is connected to the negative terminal of high tension battery, whereas the anode is connected to the positive terminal of high tension battery. This is a high tension battery. Again, let me tell you, the tension stands for voltage. So this battery provides a high voltage. So this cathode, which is represented by letter K, and this is the anode, are at high potential, high voltage. Okay, so due to the high positive potential at anode, electrons are attracted towards it, and they are made to pass through this fine hole. As a result, we get a fine cathode ray or fine electron beam out of this, which when is made to fall on this end. Due to scintillation effect, it produces a light spot that can be observed from outside. Okay, then next, let me tell you on what principle this method works. Here, we know a cathode ray is deflected by electric field and magnetic field, which is the principle behind the working of this method. Okay. Here, to produce electric field, two parallel metal plates are used here, which are connected to a power supply. So suppose this plate, this upper plate is connected to positive terminal, and the lower plate is connected to negative terminal, means it will produce electric field which will act from upper to lower plate. Okay, here this arrow mark represents the direction of electric field. Let's say I represent the electric field by letter E. Okay, then a strong uniform magnetic field is also produced here with the help of electromagnets. Okay, now let's see, this is the magnetic field representing letter B, which acts exactly perpendicular to the electric field. Okay, and I told you this magnetic field is produced by a strong electromagnet. Got it? So this is the station. Now, we know cathode ray is deflected by electric field and magnetic field. Then why this cathode ray doesn't show any deflection? The reason is the magnitude of magnetic field and the magnitude of electric field is equal here. So the cathode ray or electron beam do not show any deflection. Okay, without any deviation, it incident on the other end of the discharge tube. Understand? Okay, let's go ahead. Now first I am going to find out the velocity of cathode ray. Velocity of cathode ray. I am going to determine the velocity of cathode ray. For that, I must know the electric force and the magnetic force experienced by the cathode ray. Here, electric force experienced by electron is found to be equal to the magnetic force or force due to magnetic field. Magnetic force experienced by electrons. Okay. Now, in the first chapter of 12th physics, we have studied that the electric force experienced by any charged particle is obtained by multiplying the electric field with the charge. Here, E is the charge of electron. Okay, and the magnetic force experienced by any charge, moving charge, is given by magnetic Lorentz force, which is nothing but the product of magnetic field, charge of the particle, and the velocity with which it is traveling. Okay, here E is the charge of electron. So both sides E is common, so it gets cancelled here. And what we obtain is nothing but this. We obtain this. V multiplied with B equals to E. Okay. Now, on a cross multiplication, the value of V is obtained to be equal to. So from here, let me write this formula here. E is equal to BV. Now from this, if I keep V here as such and bring B this side, I'll obtain V to be equal to E upon B. Okay, it is multiplying here. When it is taken to the other side, it will divide. So I rearrange this. I write this equation as V equals to E capital E divided by B. Okay, this is the expression for velocity of a cathode ray. I box this for better visibility. I name this equation as equation number 1. Okay, now we determined the velocity of cathode ray. Now I am going to get the expression for a specific charge. Second, determination of a specific charge. Specific charge of electron. Okay, see how I do it. Here, told you the cathode is connected to negative terminal, so it have high negative potential. Electrons have a negative charge, so they are repelled. No, they are repelled out with some velocity. So here, electrons at the cathode accrues a potential energy, which turns into kinetic energy at the anode. So the potential energy accrued by electron, potential energy of electron is obtained by multiplying the charge of electron with the potential or voltage, that is V. Okay, and the kinetic energy of electron at the anode, okay, is nothing but half m. Here m is the mass of electron, half m v square. Here v is small v. Small v stands for velocity of electron with which it is traveling here. Okay, through this anode. These two things are observed here. Actually, here potential energy of electron is getting converted into kinetic energy of electron. So we can equate these two equations. On equating these two equations, equate, then EV equals to half m small v square. Okay. Now what is my aim? My aim is to get the value of E upon m. Here I have E, at this side I have m. So what I will do, I'll take m this side. So see, m is taken this side, so it divides, and a v is brought this side. Capital V is brought this side. So half v square, small v square upon capital V. You should not get confused between these two. Here small v stands for velocity and capital V stands for voltage. Okay. Now I box this for better visibility. The next, what I'll do, I name this equation as equation number 2. Now, in equation 1, we have obtained the value of V, the value of small v. Okay. So I'm substituting equation 1. Substituting 1 in 2. What I'll get if I do so, I obtain this E upon m equals to half in the place of V I write its value, that is E upon B. Now before I do so, for better understanding, I write the capital V here along with the 2. If I do so, what remain outside? What remain outside is nothing but V square. Now I am going to substitute the value of V. Now it will be easy if I do so. Okay. So E by M equals to 1 divided by 2 multiplied with the V, capital V. And small v, the value of small v is E upon B. E upon B. It is a squared. Okay. Now this can be expanded and written here as E upon M equals to 1 upon 2V E square upon B square. This is the expression for the specific charge of electron. Now here, if we substitute the value of these terms, then it is found that the specific charge of electron to be equal to substitute the value of all these things. So found to be equal to 1.7 into 10 power 11 coulomb. Coulomb is the unit of charge. Coulomb per kilogram. Here kilogram is the charge of, the unit of mass. This is the value of a specific charge of electron obtained if we substitute the value of all these terms present here. Understood? So this is how we obtain the specific charge of electron. Now, before conclusion, I am going to turn off the magnetic field. If I do so, then the cathode ray will deflect. It will experience only electric force and it will deviate from its path. Okay. So let me show you what I get if I do so. Now before that, I box this for better visibility, and I am going to name this equation as equation number 3. This equation number 3, which represents the specific charge of electron in the presence of electric and magnetic field. Now I am going to apply only electric field. Okay. Only in the presence of electric field. Only in the presence of electric field. Right? When only electric field is present, then the cathode ray will experience electric force. Electric force experienced by the cathode ray is obtained by multiplying electric field with the charge of the electron. Okay, this is what electric force. This is a electric force. Electric force experienced by cathode ray electron, in simple words. Okay. Now what do? I denote it by a notation. I use this notation for electric force. I use the notation of E is equal to E multiplied with small e. Okay. Box this. Okay. We will take as equation number 4. Then we know, according to Newton's second law, any object which is under motion can be expressed as, according to according to Newton's second law. Newton's second law. Any object under motion can be expressed as F equals to mv. This is Newton's second law. Okay, this gives the expression for force, no, which has made an object to move. In our case, the force is nothing but electric force. So I write Fe, because of which the electrons are getting accelerated. Here, electrons are getting accelerated. So I write, in the place of E, I write AE, and here M stands for mass of the electron. Okay, this is taken as equation number 5. Here, equation 4 and equation 5 both represents the same force experienced by electron. So we can equate them to get the expression for a specific charge. Now I compare equation 4 and 5. By doing so, I get this. MAE equals to E multiplied with small e. Here, I keep the value. I keep AE here as such, and M is taken to the other side. So I will get E upon M multiplied with the capital E. This is what I obtained. Okay. Now this represents the acceleration of electron. Represented later by equation 6. This is taken as equation number 6. I box this. Okay. Now before I proceed, let me show you what happens inside the discharge tube when we turn off the magnetic field. When the magnetic field is turned off, which is, suppose see, this is the metal plates used to produce the electric field. In this case, this is the path of cathode ray in the presence of electric field and magnetic field. Once we turn off magnetic field, the cathode ray deviates from its path and starts moving towards the metal plate which carry positive potential, okay, which is connected to a positive terminal. So this is the deviation that you can observe here. Earlier, cathode ray was traveling in this manner, but now it has deviated from its path. This is the another end of the discharge tube. Okay. Now you can see it has deviated from its previous path. Now here the deviation is shown by represented by this displacement. Here y dash gives the displacement between the original path and the deviated path. Okay, and a similar way on the screen when it is viewed from outside, the displacement is shown by letter y. Right. And the next thing that I forgot to mention, I should have mentioned this at the beginning. Here, the length of this metal sheet, the length of the metal sheet is nothing but L. Okay, So the cathode ray travels a distance of L through the electric field. Okay, this is what it means. It is so. We know this. We know velocity. Velocity V is nothing but displacement divided by time. That means the rate of change of displacement is velocity. Okay. In our case, the displacement, the distance covered, and that is the displacement covered by the electron within the electric field is nothing but N, which is the length of the sheet, and the time is taken as T here. So from this expression, T can be obtained by cross multiplication. So T is equal to L upon small v. I box this, and it is taken as equation number 7. Clear? Now, to get the expression of specific charge, that is E upon M, I am going to use the second equation of motion. What is the second equation of motion? In 11th physics, we have studied second equation of motion. Equation of motion. Second equation of motion is nothing but S equals to ut plus half at square. In our case, S is nothing but y dash. S is the deviation in our case. S is a y dash, and u is the initial velocity of electron, which is nothing but a 0, and it is the time. Let's take an as such. So half, in the place of a, I write ae, which represents the acceleration of electron. Okay, everything is same here. So here we know the value of ae, we know the value of t. Okay, but what is u here? Already told you here, u is nothing but 0. The initial velocity is taken as a 0 here. Okay, now by substituting the value of u, t and ae, y dash value can be obtained easily. Substituting u, ae and t values in the above equation. So what I get? I get this. Y dash equals to 0 multiplied with the t is 0 plus half a is E upon m multiplied with capital E, and t square is what? L upon v whole square. Okay, this is what we obtain here. Here, this whole term becomes 0, so it can be neglected, it can be removed. You have to mention that in the next step. So y dash equals to half E upon m multiplied with capital A. Now I expand this. To expand, what I get? L square upon v square. Here it is a small v, and we know the value of a small v, which is nothing but E upon b, capital E upon b, the velocity of an electron. Okay. So the next step, I am going to substitute the value of v here. V is E upon b. This I am going to substitute here. So y dash equals to half E upon m, then E inside L square, then 1 divided by, in the place of V I write E by B, E square divided by b square. Okay. When I take this to the numerator, so what will happen? B square will go to numerator and e square will come down to the denominator. Okay. So the next step, get half e upon m multiplied with e l square. Now b square goes to numerator and e square will come down. Okay, now let's see what happened. E and this get cancelled. The next step, now directly I'm going to skip one step here, and I'm going to write the value of e by m. I keep e by m one side and remaining terms are taken to the other side. So, or else I want to do so, I'll write the value of y dash. So what is that? It is half e by m. So l square b square upon e. Okay, this is the value of y dash. Now here, one thing you must know. When the spot is observed from outside, the deflection is found to be equal to y, small y. Here small y value depends on y dash value, which is the deflection inside the tube. Okay, so here y is directly proportional to y dash. Now when I remove the proportionality, I have to include a constant here. The constant is nothing but c. Here c is the constant. We call this constant as constant of proportionality. So the value of y found to be equal to c multiplied with the value of y dash, which is nothing but half e by m l square b square upon capital E. This is the expression of y. Now the next step, I am going to get the required value. No, that is nothing but e upon m value. This one, I box this for better visibility. Now let me write the expression for specific charge from this equation. Before doing so, I named this one as equation number 8. So I will make a small modification to equation 8 to get the value of e upon m. Now, before doing so, let me write this here as such. Y equals to c multiplied with half e upon m l square b square upon e is equation number 8. Okay. Now our aim is to get the value of e upon m. So I keep this term here on this side, whereas other things are taken to the left hand side. So on the left hand side I have y already. When c is brought, it will divide. Then 2 will multiply. Will go to numerator along with the e. Then l square multiplied with b square will come down to the denominator. So this can be rearranged and written as e upon m equals to 2ye divided by c l square multiplied with b square. This is the final expression of a specific charge of electron. Okay, this is named as equation number 9. Now, if you substitute the value of the terms present here on the right hand side of this equation, then it is found that the value of specific charge of electron to be equal to 1.7 into 10 power 11 coulomb per kilogram. So this is exactly similar to the value that we have written earlier. This is how one can easily obtain. This is how J. Thomson obtained the expression for a specific charge of electron. I hope the video is useful. If you have any kind of doubt and relevant to the topic, kindly put your questions in the comment section. Thanks for watching.